Hello everyone. Today we will discuss the case of AC applied to a series LCR circuit. In this, what we are going to do is we are going to draw a phasor and then a phasor solution for the impedance and the voltage and the current. So for this we know that this is your L, this is C and this is the resistor. The AC is applied to it, which is E naught sin omega t. We know that in an inductor the voltage leads the current by pi by 2. In case of capacitor, the current leads the voltage by pi by 2. And in case of resistor, the voltage and current are in same phase. We are going to use this concept to draw the phasor first and then the phasor solution. Let's first draw for resistor. For a resistor, the voltage and the current are in same phase. So these are the peak values of voltage and current, and this angle will be omega t. And since I am writing this current for all, the current will be same everywhere in all the components. So this will be taken as a common parameter of current for all the three devices. But voltage across resistor, I'll mention it by E naught R. These are the suffixes, okay? And similarly, let's mark this by right. And in case of an inductor, voltage leads the current. So current is the same for all the three components. So voltage is to be drawn separately for inductor, and voltage leads means this side by pi by 2. So this is the voltage across inductor. So this is the peak value of voltage across the inductor, because this is the phasor which represents the peak values. And if we are talking about the voltage across capacitor, it lags behind the current. So this is current. So voltage will be this way. In the phasor which I have drawn here, the inductor is dominant, or you can say the voltage across inductor is more than voltage across capacitor. That's why I have drawn a longer line to show that the magnitude of the voltage across inductor is more than the magnitude of voltage across capacitor. Now, this is 90 degree and this is also 90 degree. We'll use vector laws here to find the resultant voltage, because here the phase difference between the voltage and current for inductor is pi by 2, where the voltage leads the current, and for capacitor the phase difference between voltage and current is pi by 2, but here the current leads the voltage in capacitor. So that's why we need to use the vector laws to find the resultant. Now, as per the vector law, if we have three vectors, A, B and C vector. Then in order to find the resultant of these, we can, because these are in opposite directions, so the resultant of these two can be B vector minus A vector, and the resultant of these two can be calculated by using a parallelogram law. So this will be the resultant here. This is B minus C vector. So this way, if I have to find the resultant of these three, I'll first find the resultant of these two. So this is greater, this is less. So their resultant will be the difference of this and this somewhere. So this will be here. This will be where voltage across inductor minus voltage across capacitor. Now I have to find the voltage, resultant voltage of this and this. This will be a parallelogram. So if I complete this parallelogram, this will be this, okay, and the resultant will be along the diagonal like this. And this resultant can be written as E naught, which is the peak value of the resultant voltage, because this is the total voltage which is applied across a series combination of these three. So the resultant of the peak values of voltage across inductor, capacitor and resistor must also be this peak value of the supply voltage, which is the AC. Now let's see how do we find the angle of the resultant. We find the angle of the resultant by this. So here the angle of the resultant with one of the vectors is phi, right? And then this is equal to this, so we can write down VOL minus VOC. Now from here tan phi can be written as VOL minus VOC upon R, because VOR, voltage across resistor, because this is the voltage across resistor. If you want me to draw the diagram once again, so this is VOR, this is VOL minus VOC, and this will be the resultant phi, and this is the voltage across, the total voltage across a combination of these three. So from here tan phi will be perpendicular upon base. So where phi is the phase difference between the current and the resultant voltage. So phi is the phase difference between I naught and E naught. If I am saying I naught and E naught, then we can say that this will be the phase difference between ERMS and IRMS. Right? So this gives us the phase difference value. Now as per the diagram, I can write down this hypotenuse square. I can write this as figure 1. This is figure 2 and this is also 90 degree, we know this. If this is 90, this is 90, this will also be 90 degree. So from figure 2, hypotenuse square is equal to base square plus perpendicular square by Pythagoras theorem. So hypotenuse is how much? E naught. So you can write down E naught square is equal to base is V across resistor square plus perpendicular is the resultant of this VOL minus VOC whole square. So E naught will be under root of V naught R whole square plus V naught L minus V naught C whole square, right? Now here comes, you can write down this in terms of current. So therefore E naught is equal to under root of I naught R whole square plus I naught into XL minus I naught into XC whole square. We know that here XL and XC are inductive and capacitive reactances respectively. I can place this I naught square here, and here I can write R square plus XL minus XC whole square. Because I am taking this I naught square, I can increase one step here. If I am taking the, I want to take this I naught outside, I have to take the square along with it, right? So that's why I have written this extra step to make it clear. Then I have taken I naught square common from here. Then I have this I naught outside the root sign, and this will be under root of R square plus XL minus XC whole square. And from here I naught can be written as E naught upon under root of R square plus XL minus XC whole square. So if you compare it with the Ohm's law equation, V is equal to IR, you can say that here under root of R square plus XL minus XC whole square can be written as Z, which is called impedance. What is impedance? You can see clearly here, this is inductive reactance, this is capacitive reactance, this is resistance. So all these are oppositions to the current. So that means whatever this quantity is presenting, this is the opposition to current. So this Z or impedance is the opposition offered by a circuit having L, C or any combination of LCR, right? So where Z is impedance, impedance is the opposition offered by an LCR or LC or RC or RL circuit to the flow of current through it. The SI unit of impedance is also ohm. Right? And sometimes you are asked to derive this impedance value from the impedance triangle. So when we draw a comparative diagram, instead of voltage form in the resistance form, so this will be resistance, this will be XL minus XC, and this will be impedance. So from here also you can write down Z square is equal to under root Z square is equal to R square plus XL minus XC whole square, and here also tan phi will, this is tan phi will be XL minus XC upon R. So impedance Z is equal and tan phi is also written in this form like this, XL minus XC upon R, right? And this diagram is also called as impedance triangle. This is impedance triangle. Okay, so from here the expression of current is here. If I want to write the expression of current in RMS form, so you can write down I naught divide equation by 1 by root 2. So you will get I naught upon root 2 is equal to E naught upon root 2 upon under root of R square plus XL minus XC whole square. So this will give you I RMS is equal to E RMS upon under root of R square plus XL minus XC whole square, and this can also be written as this, and this can also be written as E naught upon Z, right? Now what if the voltage across capacitor is more? Then what will happen? If the voltage across capacitor is more, the resultant will be in this direction, and resultant of these two will be in this direction, and the voltage would have been this way. So in that case, current would have led the resultant voltage by some angle phi. So we have taken the case when voltage across inductor is more, so that's why our voltage resultant comes out to be on this side, right? So this was all about the basic concepts regarding the phasor for calculating the phase relationship between the voltage and current in case of series LCR circuit when AC is applied to it. That's all for now. Have a nice day.